Hey everyone, this is Matt with Learn Everything About Design, and in today's video we're going to be walking through a project with the Revopoint MetroY Ultra CMM. When we did the first video on this last week, some of the comments were saying it's basically an unboxing video. How do we know that this thing actually works as performed? And those are all valid questions or good questions. Sometimes when I do these videos I forget that not everybody has watched the other Metro videos that we've done. And the short of this is it behaves just like all the other scanners. The process of using it is not really any different. This scanner just is a bit faster, a bit more accurate and precise, and it has a couple of extra features like the ability to do color scans on the turntable. So what we're going to be doing in this video today is we're going to be walking through scanning this part. So this was our 4-into-1 turbo collector we designed in a video series a while back. We had this one machined by PCBWay. This was all done in Fusion, and in the review video for the MetroY Ultra CMM, I had this part, I scanned it, and then I took this into Revo Design with the 3D CAD file, as well as the scan file. This was provided, the scan file, and the thermostat housing from the 4G63 was in the downloads in the description of the video. As with all those videos, keep in mind that we are an affiliate for Revopoint, so we do have an affiliate link currently until August 31st. There is still a sale going on, so if you're watching this and you do want to buy one, you can use our discount code that stacks on top of the sale and use our affiliate link. It does help out the channel. But always keep that in mind. I try my best to give you my honest opinion and just focus on how the scanners work, rather than trying to sell you on them. So if this is the right scanner for you, that's great. If it's not, it's no big deal. So in order to get started, the first thing we need to do is unbox the thing. Now I'm not gonna go through the whole process of talking about all the parts inside, but something to keep in mind is that this scanner can be wireless. I'm not gonna scan with it wireless, but the kit does come with the battery handle. I do often prefer to scan with it plugged in, and just for the simple reason that I don't have to worry about charging the battery handle. I don't have to worry about connecting it to the Wi-Fi. It's not like it's a difficult process, but it's just an extra step. And so in this case, I've got the power plug here because we do, with these class 2 lasers, we do need to provide additional power. It can't power it off the USB-C connector. So there we go. Just got to plug it in, and then that is going to feed into the cable. And so again, same as the other Metro scanners, not really anything different here. You feed it power, and then this goes into the scanner. It's actually a fairly long cable. As the versions keep going, I feel like these cables are getting longer and longer, which is great. The first Metro X, I felt like the cable initially was a bit short. But something to keep in mind, none of these have any sort of additional relief at the laptop. And so you want to be careful that you're not putting a bunch of weight on it. You're not hanging the power brick down or stepping on it. At the scanners, they always have a little plastic latch or hook, so they do tend to hook in pretty firmly. So I'll just get that hooked up. Once it powers on, it will begin the process of recognizing it in the software. Go ahead and just put that down there. And we'll get everything set up. So in order to do this, we're gonna have to be working inside the software. So let's go ahead and zoom in a bit on what we're doing so we can see the setup and how everything is going to be placed when we start scanning. So the first thing that you want to keep in mind when you're scanning anything is that you want to make sure that you have enough marker dots, because anytime we're scanning with lasers on anything but the Trackit or the Trackit SR, we need to have marker dots. And so we've got this little piece that I 3D printed. It's got some spheres on it or some little domes. It's got these little pyramids, and I put different size marker dots all around it. And this also has these little extruded rectangles. And this is all really just for alignment. This green will show up, and so it can scan all these features and the marker dots, and it all helps with making sure that we stay aligned. I also have just this big plastic plate. On one side, I've got the large marker dots. On the other side, I've got the small ones. You always want to make sure they're at random patterns, not patterns, but random spots across here. That way you can help out with the tracking. If you have some sort of like normalized pattern on here, then you're going to lose tracking. I have recently just been setting this green one on top of this just for a few extra marker dots. It also does tend to pick up any marker dots that have come off and they're on the bench here. They do tend to stay there, and so that does help with tracking as well. The next thing is anytime that we set something down, we need to be mindful of the bottom and whether or not this is going to get picked up and the mesh is going to be one piece, or the point clouds are going to be one piece when we scan it. And so generally what I like to do is space this up with either bolts or in this case I don't have the marker kit down here in the garage, but just like little plastic caps, you can set these down and just have it floating above so that way you can scan around. We can't ever really get more than about 45 degrees away from the marker dots, so we're only ever going to be able to do the top and roll around to the side. The scanners in general want to be perpendicular to whatever surface you're scanning, and so if we're trying to, don't touch it, if we're trying to scan the sides, we're going to be completely parallel with the marker that I have here. Even though I've got these little pyramids, it's not going to be enough. So we can only ever really get to about 45 degrees, which is why we're going to flip it over. So now that this is set up, this is a stainless steel machined part. It's not prepped in any way. It doesn't have scan spray on it. We're going to scan it in a shiny mode. And so we're just going to start a new project. I'm going to go ahead and call this Tcollector, if I can spell. Another thing to keep in mind, this is true with a lot of these class 2 lasers, scanners, especially with the Track It and especially with the Metro series, they want to be at a certain temperature. If they are too cold or too hot, the results can be skewed. So you do want to make sure that when you're scanning with the scanner that it does come up to temperature. This is too low. It says it's at 21C, but I don't have a lot of time, so I'm going to just scan with it cold. But just keep in mind that it does tend to affect the results, so you want to make sure that it is up to temperature. Scanning with it for about 10 minutes will get it up to temperature, so a couple of quick pre-scans, and then you can go back and redo it. That generally helps. Just leaving it running will also allow it to come up to temperature, but it takes a lot longer if you're not actually scanning. So first thing that we want to do is we're going to be using marker scanning. We can do this with marker tracking or global marker. Global marker is going to be better because it means you can move around a lot quicker and more freely. So it feels more responsive when you're scanning, first of all, and it really helps with tracking. So selecting global marker, doing a new scan. Benefit of this too is we can reuse this when we flip the part over. We can just do that single global marker file. So with this, all we're doing is we're picking up the markers. So we'll start, we'll hit play. We'll just move around until we get all the markers. Again, you do want to be mindful of the distance. Rotate the scanner around, so if you need to get any of the little pyramids. And once you feel like you have all the marker dots, hit play again to pause it. And then we're going to select complete. Now, once it's complete, the next step for us is to double check our settings. I'm going to be using a target point distance of 0.3. That's kind of the standard. If you go lower than that, then it's going to take longer to get the scan on the screen to change colors. If you go higher than that, it'll change colors and scan quicker. It doesn't necessarily mean that you're going to get a good or bad scan. It just is going to indicate how long it takes you before it tells you you've collected enough points. So we're going to use crossline, high accuracy. I'm going to use metallic shiny object because that's what I have here, a stainless steel machined part, and then we'll select cloud scan. So Cloud Scan is using global markers. Right now, the depth exposure and everything is fairly low. I'm going to turn it on auto and just let it pick what it wants. And then I'm going to hit play and I'm just going to move around. Now you can see I'm getting about 88 frames a second. This does tend to vary based on your specific computer, of course. So if you have an appropriate NVIDIA card, you can use GPU acceleration. We are using GPU acceleration for this. If you do not have an NVIDIA card that is supported, you're going to be on CPU acceleration. And this is going to mean that you are essentially stuck at about 60 frames per second, kind of best case scenario. Because this part has chamfers on the corners, I do need to make sure that I'm at that 45-degree angle. Try to get it a little bit lower. This is going to help us with the side. It's also going to help us with inside of the transitions. This is a 3D machined part on the inside where the collectors are, and we're only going to be able to get all that from the other direction. So basically, we just want to try to get the top and all the sides and just kind of move around. Again, everything needs to be perpendicular. I could go faster than this, but I want to pay close attention to those chamfers. Those are really the trickiest pieces of this to scan. And so we're going to flip this over. Again, with global markers, we can kind of go all over and not lose tracking. That's really the benefit there. If we just had this on marker tracking, that would have instantly lost tracking. The only time we're going to have an issue with tracking in this is if I go too low and it can't see the marker dots anymore. So this is, again, about that 45 degrees. That's about as far as it can go from the marker dots. So the only sort of saving aspect of this is because I've got those little pyramids, which have about 60 degrees on them. So that gives me a little bit of an extra angle. But again, moving back and forth, what I'm trying to do is get inside of the port area, and I'm trying to get those chamfers and those transitions. When we get around the backside, it is a little hard for me to reach without getting in the way of the scan. And so I'm trying to be mindful of the green on the side because I want to be the right distance away, but I also want to be in that sort of perpendicular orientation. And again, we can just flip this around and hop to these other locations because of that global marker. Go ahead and just scan over here. And there we go. So that's probably good. While I'm here, I just want to double check the insides. I'm using this as kind of a camera. Even though I'm still collecting points, I'm just kind of looking inside. And then I'll press play to stop it. And then select complete. Again, temperature is still too low. It does take about 10 minutes. I'm going to flip this over and hope it can balance. And then I'm going to do a new scan. Again, global marker tracking. So new scan, all the same settings. Double check that it is still shiny object and that it is still global marker. Because when you do a new scan, it has a tendency to change those. We're going to use the same global marker that we got. Make sure, again, double check that it's shiny, and then do a cloud scan with the same one. Because we just flipped the part over, we can still see all the same markers. I'm just kind of saving time. And then I'll also change this back to auto. I'm just going to let it pick what it wants for that. And again, plus just kind of move back and forth. And really what we're looking for here is to get everything to be blue. And so if this setting, instead of 0.3, if this setting was 0.5, this would happen quite a bit quicker. If we set it to the low value of 0.15, then it takes longer. And all this is telling us is, it's basically looking at the points collected, and it'll tell us by the color on the screen when we get to that desired value of 0.3. And what this means is basically the distance between those points when we go to fuse these together into a point cloud. And so again, the color itself, if you keep scanning after it turns blue, you're going to get more points, a denser point cloud, and you can fuse them at a closer distance together. And so again, the number itself is really just a visual indicator for you. We'll come over here, and now because we can see the inside of those transitions, what I'm trying to do is get into these corners where I may not have been able to get in the first scan. And let's see if we can get around there. If you haven't done any scanning before, another thing to keep in mind is that these depth cameras are basically like your eyes. And so when we're scanning over edges or around corners, both of the depth cameras need to be able to see what we're scanning, or it can't tell where those points need to be in 3D. And in this case, that can get tricky, especially trying to see into small holes or over the edge of a part. So even though I'm going a little bit further away than the green bar indicates on the screen, sometimes I do that so that both of those depth cameras can see inside of that machined port area where I've got the 4:1 blending together. And so I'll just roll over here, come around the corner. And again, it's really tricky because we're trying to scan inside of this 3D object, and both depth cameras need to see. And in reality, they need to be perpendicular, and we just can't achieve that. So we're just getting as good as we can. Just get that last corner. Now, when we go to merge these two scans together, the outside is not really going to be that critical. What I'm going to be using to merge them together is the inside. And this is really because the inside is a 3D shape, and so it's only going to go one way. One thing you'll notice is the edges right here look like they're missing data. And this is because the way this is machined, we've got lines across the top from the facing toolpath that happened with a fairly small end mill. And then on the edge, it's really shiny. There's not a chamfer there or a deburr really. And so that shiny reflectiveness shows up as kind of a broken corner. It should be fine, but if we need to, we can always try to scan a little bit more in those areas. And it's zoomed way in. Yeah, I'll just cancel that. Just trying to get a little bit more in those corners, and then we'll pause it. All right, so we'll complete that. The main reason that everything has been spaced off of here is so that it's easy for us to cut the stuff out from underneath. And so when we rotate this around, you can see things are a little bit noisy, and those are touching right there, but we're going to be able to clear that stuff out. So step one is the fusion process. We're going to do high quality instead of fast, and the recommended point distance is 0.3, so we'll use that. I'm going to use a little bit of noise reduction. That takes a little bit longer, but it does tend to produce a better result. It kind of filters out some of those high and low points. So we really do want to use that to our advantage. It says estimated 10 minutes. It's not going to take 10 minutes. Usually this starts with a pretty big estimate and then it begins to wind down fairly quickly, but we'll let this crank away and we'll do the same thing to the second scan. All right, I decided to switch to my desktop for the processing, mainly because one, there's air conditioning in here, and two, when I am recording the basically in the garage, all the audio goes through the camera, which is recording 4K video, which is kind of a waste just to record screen capture. So back at the computer, what I've done is on the laptop in the garage, I fused everything together like we started, and then I did the second, well, really the first scan fused together. So we've taken the raw data and we fused them at a grid size of 0.15, which basically means if we zoom way in, what we're looking at is unified. These are kind of graphics previews of where the points in space will be. But basically, this is a preview of the layout of what we have after all the raw data. Because when you have raw scan data, a lot of times, especially when you kind of hang out in one spot, what ends up happening is you get a lot of overlapping points. You get points in the same location, and that can cause issues. So one thing that we want to note is anytime we're getting to the edge of a scan, so you can see here where we weren't able to get that chamfer on the bottom looks pretty messy. And so what we're going to do is we're going to get rid of that. And we want to be careful because the inside here actually comes down lower than the outside. That's just basically the way that this works. So what I want to do is get this to, it's like a side view. And I think I'm just going to cut all of it off. And so what I'm going to do is I'm going to cut from there, double click, and then just remove all that. Now the easiest thing in the next step is to use this option here to select connected. So just click on the top piece, it'll grab everything that's connected to it. And then all we need to do is invert that. And so we'll click the invert button and then delete everything else. And that will kind of clean that stuff up. Now that we've cleaned that up, next I'm going to go to isolation. So this is looking at basically if there are any points that are floating above or below, this stuff, basically the isolation allows us to select them and delete them. It says no data found, and that's mainly because when we went from the raw data to the fused data, there was an option to kind of take out the noise, and that's what the fused is doing anyways. The next is overlap, and so we're going to use the default settings. Doesn't look like it found much, but you can see there are some points there on the threads, and there's one over here in the corner. What we're going to do is apply that and let it remove it. And so overlap detection is looking at any points that may be above or below. I'm not going to do any smoothing or simplification. I tend to do that at the mesh level. So we're going to hop over to this scan, and I want to kind of do the same thing. This is where we have to be careful because now we certainly can't just draw a line across. We can for the bottom stuff, so I can get rid of that and double click. But for these edges here, that isn't going to work. And so generally what we do is first we'll do the select connected, because now the bottom is sort of cut off. As soon as it's connected, we can invert that. And then just delete the inverted stuff here. Then I'm going to go back to this tool, and I would really love if future versions of Revoscan had sort of an edge cleanup where it could take these and just basically just push them back a couple of polygons and just clean up those edges, because that's always a big thing. If we're trying to scan, we're always going to get those sort of messy edges on the fringe of whatever we're scanning. So all I'm trying to do here is just clean up those edges a little bit. For the sides, I can zoom in and I can just cut through like that. And on the other side, do the same thing. And go right there. Just cut it. All right, and again, we want to do isolation detection. It's probably not going to find anything, again, because we used that option in the fusion, or when we were fusing all the points together, and then we'll apply that. All right, so we have two semi-prepared point clouds, and we're going to merge them together. So we'll select both of these, and we'll see if it can do it automatically by feature alignment. I'm not going to hold my breath on this. A lot of times it'll give priority to these holes, and you can see that it didn't do a very good job. So in this case, we have to use manual alignment. And what this means is we need to manually pick points that are the same on both. And so this is where the 3D geometry comes in handy. So we'll do like 1 point here, one down close to there, one over here, and then try to find roughly the same on the other side. Now, actually, if I zoom in, is that the same? Let me rotate this around. I may need to clear the points. One of them has a little bit of a scar on it, and it looks like it's that side. Okay, so I'm going to clear the markers, and I'm going to do it again. I want to make sure that we are getting the right one, because it will use that information there. We'll go here, and give it this. As soon as we have 3 points, it'll start to try to merge them together. Now that looks a lot better. And here's, you can see why we tried to clean up the edges. There's a little bit of stuff that's still kind of messy there. I should have cleaned up, but we wanted to get all of the messy stuff away from the edges, because when we get to those edges and we merge these and we generate a model, that's going to produce some issues in the section between the two scans. All right, so now if we go back to our mesh, we now have a single mesh. We've got the little lip. There's a little kind of thing on the scan here. There may be just a little piece of dirt on the actual part, but everything looks pretty good. And you can run overlap detection again. Now that we've got a merged scan, it'll probably find a lot of common points. You can also run isolation. It shouldn't find anything because, well, maybe it found a couple because it didn't give me an error, so we'll select apply. But generally, the overlap detection is the one that brings back a lot in that second go around. So now we're going to turn this into a mesh. And so we've got fast mesh and high quality mesh. We're going to use high quality, and then we've got to choose a grid size. This is going to be where you are going to end up with a really dense, high number of polygon or triangle mesh if this number is small because this number is high. Now, if we go higher, basically this grid size gets smaller. If we go lower, it's going to get bigger, and so on. You can always redo this step. So we're going to apply it at what it came in at, 7.5, 7.6, and we're going to let it figure that out. Note that on my desktop here, the NVIDIA card that I'm running is not supported. So it's running on CPU acceleration, but you can still see that didn't take very long. All right. There are a lot of what look like surface defects on here, but the part itself, this is a good example right here. This is actually a milling mark that is present on the surface of the part. And so all these lines that we see going left and right, those are actually the remnants of the facing toolpath. And my guess for this is this was some sort of feature or section of the raw stock they left to hold the part to machine it, and then they went back and cleaned it off afterwards. It's actually a section where you can run your fingernail over it and you can very clearly feel it. So if I was concerned about this and I had a machine in my garage, I would chuck this up and I would face the back side of this so it's nice and clean. In reality, it's not really going to be a problem. I could take like a deburr type wheel on a Dremel or on an air tool, and I could clean that up as well. I'm not concerned about it for the part itself, but that's why that is there. That's actually machining marks. But what we want to do from here is we want to simplify this a bit. So we're going to go to display. We're going to go to a mesh model display, and we're going to do wireframe overlay. So when we zoom in, this is how dense we are right now. And so what we want to do is we want to clean this up a little bit. So first step is double check isolation. Make sure there are no floating points that have kind of worked their way through. And then we have the option to smooth. If you do this, I would say leave this on solid so you're not focused on the triangles. Be real careful with the strength. And I generally would do more times through and lower strength. So the strength value is essentially the distance that it can move the points up and down, or the triangles up and down. The times is basically the number of iterations you run through it. So if we apply this 8 times 0.1, pay close attention to like the machining marks, you can see everything gets softer. Where you want to be careful is where you have sharp corners. So in this case, if we look at the threads, so what I'm going to do is I'm going to undo this and look at the thread display and then this little lip we have here. Now in reality, that's a sharp lip. We're never going to get a perfectly sharp corner on the scan, but that is a sharp lip. And so if I were to kick the strength way up and say apply, pay close attention to these corners and close attention to these threads. You can see they're just kind of getting softer and softer. So I tend to avoid smoothing, and I opt more for simplification. And so I'm going to show the wireframe overlay again. I'm going to go to simplify. And this ratio is going to be basically a percentage of the original. So right now, let's look down here. We've got 1.1 million polygons. So if we set this at 50%, we're going to take that down to 600,000 polygons. And with this process, it can take a little while depending on your model, but it generally does a pretty good job of leaving high density meshes where it needs, and then lower density on the bigger faces. So if we kick this, let's just kick it way down. Again, we can undo this and we can remesh whenever we want. So there's not really any penalty to trying this. But the more we do this, we're down to 491,000. And if I go to display and just show the solid again, the threads still look pretty good, not that I need them. And this corner looks pretty good. Surface details in there look pretty good. And you can continue to do this. You can keep refining it. And then as we do this, more so than smooth, you'll notice it doesn't have a huge negative impact on these corners. And you're eventually going to get to a point where you've got a really lightweight mesh model that still has all the features that you need. So right now we're at 100,000 polygons, down from 1.1 million. And so this probably has more than enough detail for us. And if we bring the display back, do the wireframe overlay, you can see the triangle size is quite a bit larger. And then it's just a bit denser in these corners. And then if we go to the, well, let's zoom out. Let's go to the bottom. Maybe go into one of these threads. Looks like there's a tiny little hole there. But you can see here it's putting the density of those where it's needed. You can also go to fill holes. And in this case, because most of them are going to be planar, I'm going to leave the plane method. I'm going to detect holes. And so this is probably just maybe a graphical error. It's not a real hole, or there's maybe an overlap issue there. But we can run simplify one more time. I'm going to get this as light as possible. Look, we're down to 63,000. And if we go to display and go back to solid, I'd say that looks pretty good in terms of what we need if we were trying to reverse engineer this. Of course, you would have the physical part and manual measurements. You generally don't need to send a 1 or 2 million polygon mesh into like Fusion, or if you're going to be doing some work with it. You can make that quite a bit smaller. You just need to be very mindful of things like how smoothing impacts that mesh versus how simplification does. It's reducing the triangles, but it keeps the density where it's needed. And so now that we're, essentially we're done with this, if we want to do any more work, we do have the ability to do some additional processing, like smoothing out specific areas. We do have a smoothing brush. And so, for example, I can come in here and just clean up that one spot that may have been a problem, and everything else looks to be pretty good. And so just taking care of that one spot, whatever, if it was dirt on there, whatever the case might be, we can just kind of clean that up before we send the model out. And once we're done with it, we just export it, right? So then we're going to send the mesh model out. The origins aren't going to matter because I'm going to use QuickSurface to align or Revo Design to align, and then I'll just save it in the same place. All right, I will throw the download link for this in the description of the video if you want to take a look at it. But again, just to make sure we understand the process, and I'll mention this again in a minute, but the process is going to be the same across the board for the MetroY scanners and the Metro X if you're not using them in a wireless mode. And you're picking a marker scan, which can be markers or global markers, or a feature scan, which is going to use the texture and the shape on the object for tracking. Feature scan is only available for full field mode. It's not available for laser scanning. So that would be on the MetroY Pro and the Ultra and the Ultra CMM, because the MetroY base model only has laser scan mode. The Metro X series has feature scan and full field mode as well, so you could use it there. For marker scanning, you can use that for any of, basically you can use it for any of the modes, any of the three laser modes, and you can also use it for full field mode. And there is a turntable mode as well. And so those are just something to consider. But again, the workflow is going to be the same. Revoscan across the board. Revoscan 6 looks a little bit different. That's not currently supported across all the scanners. So it doesn't support the Metro series of scanners or the Inspire 2, I believe. It does support the Pop 4, which is where we saw it, but hopefully the UI and things will change across the board so it's consistent. But right now, this is what all of the Metro scanners UI is going to look like, and that's the workflow that we're dealing with. All right, so let's hop back into the garage and let's wrap this up. All right, you know what, since we're here, let's go ahead and let's change tact a little bit and let's show RevoMeasure as well. And so I wasn't planning on doing that, but let's go ahead and just walk through it. So that way anybody that's interested in the MetroY Ultra CMM can at least see what Revo design is. So once you have a mesh created inside of Revoscan, we have the option to export it like we just did. You can export all the models, just the point clouds, just the mesh. If you did capture color data, you can export the texture as well. We did not in this case because we would have to use the turntable and laser mode to get color on the MetroY Ultra. But then the next one over here is a third party. So once again, Revo Design is a rebrand of QuickSurface Lite that you can buy through Revopoint. You can attach it. There are variations of each of the Metro scanners where you can bundle them together and save. RevoMeasure is a program that Revopoint came up themselves, and this is a CMM style tool where we can measure our scan data, we can bring in CAD data, and we can compare them. And then Geomagic Control X, again, it's another program similar to QuickSurface Lite that is dedicated for mesh processing. So what we're going to do is we're going to send this to RevoMeasure. And again, RevoMeasure it's not a rebrand to the best of my knowledge. This is a program that Revopoint created themselves. And the goal of this is to allow for additional measurements, extraction of primitives, and to be able to compare CAD data to your scan data. And so this is a part that we designed in a series where we created basically a 4-into-1 T4 style turbo collector. And so now we have the CAD model. I can import the CAD model into here. And once we have it in, you'll notice that the CAD model is aligned to a coordinate system. However, the mesh is not. So the first thing that we do here is we go to comparison and we try an automatic alignment. This I have found works really well. And this part is symmetric. You know, it's symmetric across the XZ plane in this case, as well as the YZ plane. And it does a really good job of just automatically aligning it. Because the CAD data was aligned to a coordinate system, you can see it moved the mesh. So now our mesh is aligned to that coordinate system in here. But keep in mind that the idea here is not to export mesh data from this. We can generate reports and we can, work with the mesh data and the CAD data in here, but it's not meant to align to a coordinate system and export that data. But what we want to do here is we want to compare the CAD data to the scan data. So first thing after the alignment is to check the deviation. And you can do this as an overall deviation or specific point deviation. And so what we're going to do is we're going to start by selecting overall deviation. We can use tolerance. If we need this to be, let's say plus or minus, let's say 0.4 millimeters, and we'll change this one to 0.4. We can also display a min and max, and we'll create it. And so what this does is it gives us a calibrated color bar. Anything that's between the tolerance range that we set, in this case plus or minus 0.4, will show, in this case, everything is green. Everything is within that tolerance, with the exception of the areas where the holes are threaded. And the reason for that is because a CAD model typically is not going to include modeled threads, especially when it's a design that's meant for CNC machining. When you're 3D printing, you'll have modeled threads if you need to actually have the threads included in the print. But with CNC machining, the hole size is actually the tap size. So for example, a 1/4 inch or 1/4 by 20 bolt, the hole that you drill is 0.201, right? And so that is basically the root diameter of the threads. And so it is going to be off in the threaded areas because the CAD model doesn't include those. but everything else is well within tolerance. You can see that plus or minus 0.4. And you can change these values. Again, you need to decide what the tolerance values that are acceptable for you are. And, let's say that we set this to something a bit tighter, let's say 0.05 on the negative side, and we'll go to 0.05 on the positive side, and we create, and now we've got, let's go ahead and hide that one. And now you can see it's not all green anymore. So most of it is within plus or minus 0.05 millimeters. So again, remember this is in millimeters, not inches. So plus or minus 0.05 millimeters, and then the yellow areas are about 0.1 millimeters. So if you're working in the inch unit system, that's like 0.004 inches, right? So this is well within tolerance. And remember, this part had a bunch of machine kind of artifacts on it. It was faced with a small end mill rather than a big shell mill or a fly cutter or something like that. And so there was a bunch of, you can kind of see the lines going left and right on it. And you can kind of see that it is just slightly off from the CAD file. Now, one thing I will note is that the top on this side here is green and the bottom is yellow. When we rotate it around, the top is green and the bottom is yellow. This tells me that it's just a little bit off, potentially not completely square or parallel, and it's likely due to the way that it was fixtured when it was machined. Doesn't really matter for this part, but just something to keep in mind that we need to consider, consider these aspects. You can also do point deviation, so you can identify, specific points. You can take a look at the deviation map color scale, and you can modify the tolerance values. And then you can also create a coordinate system that can be used for alignment and measurement purposes. So if you need to find the deviation from a coordinate system to a specific area, then you can do that. I'm going to hide the deviation, and we're going to just hide all of them. And then I'm going to go to measure. And so measure is another thing that we can do. Let me hide the CAD model because we don't need that. So another thing that we can do is create primitives and use them for measurement purposes. This is kind of a tricky part to do that, but I'll show you on, let's see if I can actually create some cylinders for the holes. I'm not sure if it's going to work with the threads, but we're going to create it from the scan data, but I want to use a smart fit. I'm going to use a brush, and I'm just going to kind of brush inside this area here and then allow it to use smart fit. Again, this is a threaded hole, so it's not going to be perfect because we're not dealing with just a machined hole. We have some tolerance values here. One thing that we can't do, at least that I'm not aware that we can do here, is force these primitives to be perpendicular to a plane, for example. Like I can't force this to be parallel to the z-axis. But what we can do is we can create these, and again, I'll do this over here. Oops. And I'll just do this for the example. And then we can measure the distance between these. So we can take a look at the size, the diameter, this one 9.002, 8.955. So both are really close to each other. And again, we're dealing with threaded data. And then we can measure the distance between cylinder 1 and cylinder 2. And you can see it's 70.021. I believe in the CAD model, it's 70 millimeters, and we can extract that data from the CAD model as well. But you can see 70.021. And then if I bring the CAD data back and I hide the scan, I can go ahead and let's go ahead and create some cylinders, create from CAD, and I'll create one there. And I'll create one here. Go ahead and just pull these over. And then I want to measure the distance between cylinder 3 and cylinder 4, 70.035. And so now we've got, it says fail because I didn't add a tolerance value, so it's trying to do plus or minus 0. But 70.035, and then if we again measure between cylinder 1 and cylinder 2, or 70.021. So that's a difference of 0.014 millimeters between the measured CAD data and the actual scan data. And I think that's pretty good. All right, I think that's a pretty good result. Some other things that we can do, I'm going to go ahead and hide these. They're showing red here because it failed because I didn't add a tolerance value. And actually, you know what? Let's go ahead and let's add a tolerance value here. So I want this to be minus 0.05, 0.05, and now you can see it's plus or minus 0.05 millimeters, and now it says that it passes. So I'm going to hide these because we don't need to see them. I'm going to hide the CAD data, bring back the scan data. Some other things that we can do is we can extract primitive planes or other features. And so what I'm going to do is just kind of draw on the face here. It's going to give me a best average. We're going to create that. We'll do the same thing on the bottom. So kind of draw here, create that. And then for that plane on the bottom, what we're going to do is we're going to set one of them as a datum. So we want to use plane 2 as our datum. And then we want to measure how parallel the bottom face and the top face are. So we want plane 1 and datum A, and we want to measure. And you can see here the deviation is plus or minus 0.3 millimeters. And again, this tells me this is based on how the part was fixtured. And for a turbo collector that's going to have a gasket, it's going to be welded on this side. That honestly, the top and bottom being parallel doesn't really matter. All that matters is that this bottom face is flat. And so what we would want to do is check things like the flatness of that bottom face. So it's plane 2. And it needs to be flat plus or minus 0.5, and we'll measure it, and you can see that it passes. And so in this case, whether or not they're parallel doesn't really matter, but whether or not that bottom face is flat, and you can see here it's 0.07, whether or not it's flat is really the key thing to ensure that it can seal to the hot side of the turbo. And so I'm going to go ahead and hide all that stuff, but that's just a quick rundown on what you can do with RevoMeasure. And again, if you do happen to buy the MetroY Ultra CMM, you get RevoMeasure for a year. You can also buy it on your own by the month, or you can buy it by the year. It is a program directly from Revopoint, so it's not a rebrand of something else. So if you do want to use this as a CMM measurement type tool, then make sure that you do look at the MetroY Ultra CMM, or that you look just for RevoMeasure and purchase it on your own. All right, so there you have it. That's the basic process. And again, the process, the workflow that you go through with the Metro X, the Metro X Pro, the Metro Y, the Y Pro, and the Y Ultra, and the Y Ultra CMM, they're all the same. All right, the setup is the same, the workflow is the same. The difference is that when you're using the Ultra or the Ultra CMM, you're getting 90 frames per second instead of 60 on the Metro Y Pro. You're getting 3 million points per second instead of 2 on the Metro Y Pro, or 1.5 on the Metro Y. You still have the same 34 cross lines. You still have the same number of parallel lines and the single line and the full field mode that you do in the Metro Y Pro. But again, you're getting a boost in speed in both the points per second as well as the frame rate. And then you do get a slight boost in the single frame accuracy as well. So 0.015 millimeters instead of 0.02. Other than that, there is not a difference in how you use it. So if you've seen any videos on how the Metro Y Pro or the Metro Y works and the Metro X or the X Pro, they all generally will work the same. Just as you go up that scale, you're going to get more speed, more accuracy. The Ys, of course, the base model Metro Y is laser only. There's no full field mode. The Y Pro and the Y Ultra both have full field mode. So again, that's blue structured light. They do come with the turntable, and so you can use it for turntable tracking for the full field mode as well as for laser mode. We've done videos with the turntable before that is a Bluetooth enabled 2-axis turntable. And so that works really well. It probably would work fairly well for a part like this that we scanned today. But I generally don't get out the turntable. I just don't use it very often. So I would need a very specific part. Generally, when I use it, it's because I have a circular part that has trouble with tracking, because on the 2-axis turntable that's linked to the software, it actually rotates it, scans while it's stopped, rotates it again, scan while it's stopped, and so on. And so that does really help with the tracking. So something to keep in mind. But overall, again, this does deliver more than the MetroY Pro. Whether that's worth it for you, that's kind of up to you to decide. They are on sale right now until August 31st, I do believe. So if you're looking to buy one, go ahead and check the description out. I'll leave all this information down there, the discount code, affiliate link, and all that. If you have any other questions on this or anything I missed, questions that you want covered, leave a comment. I do my best to see and answer everybody's comments and emails. I try to get to them as quick as I can, but that doesn't always work. But any questions or comments, leave them there. I'll do my best. And as always, thanks for watching. We'll see you in the next one.